then?
Yeah.
All right, and we'll let you start.
Okay, so I'm an assistant professor, and I co-direct the Software Engineering and Cybersecurity Lab at MSU in Bozeman. Work closely with James's group at WSU. And so why am I talking about aggregating, and why am I talking about static analysis tools? Number one, we want to be thinking about how do you evaluate how secure a software artifact is without running it, if you don't want to execute the code. So people are heavily reliant on static analysis tools.
I'll do the slides for you.
Oh, you are doing the slide? Okay, go for it.
Yeah.
So this work is led by me, and then we've got 3 students here, Brittany, Redempta, and Tom, who all worked extensively on this work, as well as Clem Azarieta, who's my lab co-director. And this work has been heavily funded by DHS, S&T, as well as the CISR program. Sorry. Okay, so Peak is one of our flagship technologies that we use in our lab. And actually, will you advance it? This is blurry. Just, okay. So, so Peak is one of these flagship technologies that we use. What we do is we take in cybersecurity static analysis tool outputs from multiple tools of multiple different flavors, CVEs, CWEs, GHSAs, you name it, and we aggregate those into measurable concepts. And so then at this level in our hierarchy, these might be concepts that a program manager would be interested in and that type of thing. And then we aggregate them further into security factors and aspects. These are high-level business goals, or like what was just being talked about. Like this might be something that your 4-star general would be interested in knowing. Okay, slide. So what's important here is that these inputs at the bottom level need to be highly accurate. Because if we have any errors or inconsistencies here, what you can see is they're going to move right on up this hierarchy. And as they move up the hierarchy, then our decisions that we make based on this are going to be impacted. Okay. So in our work looking at static analysis tools over the years, what we have found is there's several sources of variability that introduce uncertainty that keeps me up at night. I'm going to talk about 2 primary sources. Number 1 is sources of variability inherent in using cybersecurity static analysis tools in and of themselves. So this is about the tools themselves. And the other is challenges with aggregating the results, often from many tools. Okay, so slide. So first we're going to talk about goal 1 here. Okay, go ahead. So our research group has been looking at static analysis tools for a number of years here, and we've identified 6 different sources of variability. So we've got version, vendor, the configuration of the tools, how failures are handled, outputs vary widely across these tools. The dependencies that the tools rely upon can introduce all sorts of challenges, talking about whether you're pointing to the NVD or the OSVD, which of these different vulnerability databases, as well as the environment that you're running them in. So over the years, we've looked at binaries, we looked at source code, we spent a lot of time looking at C# code, looking at microservices as well as software bills of materials, and we can talk more. Or this is found in the paper. Okay, go ahead. But what I do want to talk about a little bit is some variability that's been that we've identified just as a result of varying the version of single tools. So just one tool, but multiple versions. Okay. So this is a paper that we published at IEEE, results from a paper from IEEE CSR that we published last year. And we evaluated 2 very commonly used static analysis tools for the evaluation of binary code. One is CWE checker, and the other is CVE binary tool, or CVE bin tool. These stats are from last summer, but you can see these are heavily used tools just by their GitHub stats. Okay, keep going. So what did we do? What we did is we acquired multiple versions of CWE checker and CVE bin tool, and we then gathered 660 binaries that were publicly available. These are all from a Kali Linux distro. And what's important here is we run one version of each binary through every version of the tools. So you only have one target, but multiple versions of the tool. Make sense? Okay, and then we assess the consistency in the outputs of the tools. So what we expect is that, yeah, maybe there's going to be some variability commensurate with the software development lifecycle as developers are working on these static analysis tools, but we would think that, you know, they wouldn't be wildly different. What we found, however, was that they were wildly different. If this doesn't trouble you, it should. So these are the results over here from CWE Checker. This is CVE bin tool. And each line in these stacked bar charts corresponds to one of the binaries that we found. So what you can see here is and they're colored by the numbers of vulnerabilities or weaknesses found in each. So up here in yellow, what you can see is these, I'm just going to take the extreme case here. So these up here were found to have between 3,000 and 4,000 vulnerabilities in version 0.4. And then if you follow this line down to here in this darker purple color, oh no, actually this exact same target, less than 100 weaknesses in it. So what we have seen is a lot of our government and a lot of our industry partners, what they do is they go online, they find the most recent version, they run the tool, and then they say, oh, this is the right answer. And what this is saying is that when you find or you download a new version of these tools, you're getting a new answer. And I just want to point out also that both Travis and Colleen, who worked on this, were students who worked closely with me in a summer program. Okay, so this is binary code. Let's talk a little bit about microservices. So this is work that Brittany Bowles has been working hard on. And so we're looking at both version and vendor differences now. So Brittany has gathered a large corpus of Docker images. She gathered basically every version, every official Docker image from Docker Hub, the most recent version. She runs them through two common static analysis tools for evaluating Docker images as well as software bills and materials. These are two tools that purportedly do the exact same thing. These two tools are supposed to tell you how many vulnerabilities you have in your Docker image or your SBOM. So she runs them through there, and then we get these vulnerability reports and we take a look at what we find. All right, so the first thing that you're going to see, sorry, I got a laugh in the back there, yes, is that we've got the results from Trivy here, Gripe here. The first thing you'll notice is that, so these are just the cumulative number of vulnerabilities across the corpus. The number of vulnerabilities found by Trivy is always lower than Gripe. What you see is that the number of vulnerabilities here is fairly consistent over versions for Trivy, with the exception of this, but for Gripe, we're seeing a lot of differences. If you want to know about this one, this is the big shift with CPE matching with Gripe if you're a static analysis tool nerd like I am. But the other thing to note is we're doing an extensive work on this with software bills and materials, and surprise, surprise, we're finding the same thing. So, okay, let's keep moving. So these are things that we are continuing to work on, and we're trying to find ways of establishing consistency and finding ways that we can build trust in using these tools. But this is an active area of research, and it's pretty important. So now I want to talk about aggregating the results from many tools. So this is an area where we've had a lot of success. So supposing your inputs are valid from these tools, what we do is, and this is something that I worked on heavily, and that is really important for our models because this is where we scale things. So we gather the collection of software artifacts, we run them through a bunch of static analysis tools, and we create an aggregation file. The simplest way to think about this is like a flat file. So what we have on the columns are all of the different vulnerabilities or weaknesses in code. So this can be hundreds to thousands. And then down here along the rows, what we have are our software artifacts. So for every single one of these weaknesses and vulnerabilities, as shown in here in red, we create a distribution of those findings. And then we use a little math. We use a probability density function to smooth out the curve, and so that we can calculate the area under the curve. So these vulnerabilities, remember, every tool has different scales, different ways of reporting them, but this makes it so that we get everything between 0 and 1. So then, supposing that we have a new software artifact, and you say, well, okay, I want to know how good or how bad is this? Well, it's got 40 instances of this vulnerability. Well, what does that mean? How do you know? So what we do is we use this probability density function, and we can calculate the area under the curve. And so what this shows us here is that if you look where 40 is in this distribution, you can say, well, okay, I'm doing better than 66% of the files that are out there. So as long as you have a large enough corpus of software artifacts to compare against that are representative for your domain, this is proving to be extremely useful for us. We've used this for now scoring something, I think we're at like 15 or 20,000 different software artifacts. And so this method is working really well for us. Okay. So some of the commonly encountered distributions that you will see, we often see things like this that are bimodal distributions. This is an example we looked at before. The other thing that you tend to see things that look like this with a negative binomial distribution. So here, this is the number of findings in the corpus and the frequency. And so, this is just showing you how 40 can look very different in different settings. The other thing we see is we get these constant value situations. This typically occurs, the most common constant value you get is 0. So essentially what that means is that across the entire corpus of Docker images or binary files, whatever you're looking at, there's no vulnerability or weakness found. And so then you basically, of a certain type. And so essentially what we do here is we have a special case where you say, like, okay, well, if it's greater than 0, then the score, it's going to score poorly. Okay, or greater than whatever the value is. Okay. So to wrap up, we've identified several sources of variability, those that pertain to the tools themselves, as well as aggregating findings across those tools. We see that there's high vendor and version variability as a result of the tools themselves, and I haven't even talked about configurations and everything else, dependencies and scope all layers. Keep going. However, we do have had great success with this method of aggregation as long as you can trust the inputs that are going in. Yes, James.
So, you're looking at different static analysis tools and how many vulnerabilities each one is determined. Do they produce false positives in the vulnerabilities they find at all?
Yes, so static analysis tools, this is one of the downfalls. So we actually have a paper that's going to be coming out on this pretty soon. Brittany Bowles is leading that one as well. So static analysis tools are notorious for finding false positives. And so there's a number of different ways that people get around this. And so Gripe and Trivy each maintain databases of false positives. And essentially what they do is it's like, okay, you have this vulnerability, and then, oh, it's in the false positive database, then don't worry about it. But even still, I know, you're shaking your head. It's very problematic. False positives are a major challenge. But I can talk ad nauseum, but I don't know if I'm over time or not. I try to.
Let's give Anne-Marie a hand. Anne-Marie, thank you so much.
Thank you.